And again, you can see we have another example of free undamped oscillation of a uniform stick inside a semi-cylinder. Take a look at the statement of the problem, and it is a thin homogeneous rod performs small oscillations inside a smooth semi-cylinder of radius r. Okay, right? Um, remaining in a plane perpendicular to the axis of the cylinder. That means axis of rotation of the cylinder. Though cylinder is not rotating, the length of the stick is equal to the radius of the semi-cylinder. That's right. Find the law of motion of the center of mass of the stick. That's also right. Assuming that at the initial moment of time it was at rest and was deflected from equilibrium position by a small angle phi naught. That is not mentioned in the picture. The picture is basically the solution picture. I have drawn it trying the solution. You can see here that the rod is deflected from its equilibrium position in this picture, and we are going to use the dynamic method in lab inertial frame to solve this problem. And to do this, we will consider the stick to be a rigid body, and you can see here three forces act on it: the force of gravity and both the normals, forces of normal reaction of the surface of semi-cylinder, namely N1 and N2. And we have neglected the forces of friction and air resistance. Now we can write the equation of moments for the stick relative to the axis coinciding with the axis of the semi-cylinder, that you can see here, this thing. And the axis is passing through O and perpendicular to the plane of this drawing. And you can see here N1 and N2 will not produce any torque about this axis passing through O. Only weight is going, the force of gravity is going to produce some kind of torque, and it is against the rotation. We have rotated this stick in anti-clockwise direction, and this mg is producing torque in clockwise direction. It's trying to restore the disc to its equilibrium position. So we would like to write its torque as restoring torque, that will be minus mg, and its moment we would like to write it L sine alpha. L is the distance from the axis of rotation to the center of mass of the stick, that is this. So this length is L, and so that I can write this length, the moment arm of the mg, by L sine alpha. So I'm going to write down this like minus mg L sine alpha, simply because it's a restoring torque and the other torques are absent. So I will simply write it. This torque is going to provide us the necessary angular acceleration that should be equal to moment of inertia multiplied by d2 alpha by dt square. d2 alpha by dt square is angular acceleration, I is the moment of inertia. And we can also find something else like the other information, like what is this length L? This length L we would like to find, and since this is R, and of course these are also the radius of the semi-cylinder, so it makes a equilateral triangle. So this angle will be equal to 60 degree, and this is the radius. So you would like to write the length L equal to R sine 30 degree. R sine 60 degree, sorry, R sine 60 degree, and so you would like to write it r root 3 by 2. So L becomes L, the value of L you can find here is r root 3 by 2. And let's next find the moment of inertia of the stick relative to the specified axis passing through O. And we can find the moment of inertia of this stick around the axis passing through O simply by using parallel axis theorem. And so our moment of inertia becomes ml square by 12 plus ml square by 12 plus ml square. If just put the value of L there, and you will get the value of whole thing, the moment of inertia. And I think we have calculated all the things, necessary things. So I'm going to put here nothing but the value of L, or we can take it in terms of L. So we don't need to put the value of L. You can simply put the value of I, moment of inertia, in terms of L, and then put the value of L in the resulting equation, and you will get something like I have already got, so I am not worried about d2 alpha by dt square plus 3 root 3 by 5r multiplied by g and alpha equal to 0. 3 root 3 g by 5r multiplied by alpha equal to 0. And then you can get the frequency of the rod's natural frequency, and that will be something 3 root 3 g upon 5r, and like this you can find the angular frequency. And we needed to find out the law of motion, and this you can write simply in terms of alpha and t. Alpha in terms of t you can write, and that will be a sine or cos omega t plus phi naught, like this. And if you wish, you can differentiate it once again so that it becomes d alpha by dt equal to minus a omega sine omega t plus phi naught. And at t equals 0, the initial conditions of motion were at t equals 0, alpha was equal to alpha naught. And if you put it here in this equation, you will simply get alpha naught equal to a cos phi naught, and d alpha by dt was initially 0. So you can put t equals 0, d alpha by dt was equal to 0, and you can put it this information in this equation, and it will give you something t equals 0. That means 0 equals minus a sine phi naught, that is a sine phi naught equal to 0. And then you can put all these things just by expanding. Alpha t equals a cos omega t cos phi naught minus sine omega t sine phi naught. And you can get here sine phi naught equal to 0, so this term becomes 0, and cos phi naught equals alpha naught by a. You can put here, and you will get your result simply as alpha in terms of t equals alpha naught cos omega, that means 3 root 3 g by 5r multiplied by t, alpha naught cos omega t. And this is the South equation of motion of center of mass of the stick. Thank you very much for watching.